All right, let's look at a capacitor example. So let's kind of draw a circuit out here. So let's use a battery. And let's go ahead and have a capacitor there, a capacitor there. Maybe the circuit joins back up, and then have a capacitor here. Okay, let's give these values. Let's make this 10 farads. And that's a massive capacitor, but I'm just using nice numbers. A 20 farad, and then a 6 farad. Again, 1 farad is a massive capacitor. Usually they're like microfarads or, microfarads or even smaller. And then let's hook it up to a battery of 30 volts. Again, I'm using these numbers just to kind of make all the numbers work out nice. Okay, so what are we going to do? Well, I want to know the charge here, the charge here, the charge here. I want to know this voltage drop, this voltage drop, that voltage drop. I want to know the total charge. I want to know the energy stored on each one of those, and I also want to know the energy stored for the whole system. Okay, all of those things will kind of break it down. So, what's the first thing you're going to do? Well, you're going to find the total capacitance. So, let's look at this guy first. What is the effective capacitance of this piece of the circuit? Well, these two things are in parallel with each other. We know that capacitors in parallel just add. So 10 farads and 20 farads makes that particular part a 30 farad capacitor. So how does this and this add? Well, these two are in series. So then the total capacitance of the system, 1 over the total capacitance equals 1 over 6 plus 1 over 30. And again, think about these two are in parallel, so they add. So that this effective capacitance is a 30 farad capacitor. But then this 30 and this 6 are in series, so that their combination, their effective capacitance, which is the capacitance of that whole circuit, 1 over C equals 1 over 30 plus 1 over 6 plus 1 over 30. 1/6 plus 1/30 is 1/5. 1 over C equals 1 over 5. So the total capacitance is 5 farads. Okay, so now we know the total capacitance of the system. Okay, that's a positive step. And now let's write down the fundamental. Q equals CV. Because if I know that the total capacitance of the system is 5 farads, and I know that the system is getting 30 volts, then the system has 150 coulombs of charge that can be stored. Okay, so now I know Q total. Q total because I know C total. So then the whole system is getting 150 coulombs of charge. And now you got to think, okay, how do these work? Well, just like they do in resistors. If this thing is in series with this thing, they're all getting 150 coulombs. So this combination gets 150 coulombs of charge, and this gets 150 coulombs of charge, because that's how it works. You take this battery, and it takes charges from down here and chucks them up here. So it's going to take a whole bunch of positives from down here, leaving this some net negative. Right? Let's say it's like a 6 down here, and then it's going to put 5 up here. Well, it can't put, it's going to put 6 negatives, and it's going to have 6 positives, and it's going to put some here, and it's going to put some there. And then that's going to polarize this thing and leave that the way it is, and that like this. But the biggest thing is the charge on this capacitor is the same as the total charge. Just like if it was resistors. Again, think about if it was resistors really quick. If these were resistors, most people can think resistors easier. How much of the total current goes through that? All of it. How much goes through these two? I don't know, part goes this way and part goes this way. Same thing here. How much of the total charge gets stored on that capacitor? All of it. How much on those two? This gets some, right? Charge, as it's being charged, comes this way, and some of the charge goes to this plate, and some of the charge goes to this plate, but all the charge gets to this plate. Okay, so let's look at just this bottom plate, and I can do its own Q equals CV. The charge on that plate we know is 150 coulombs. The capacitance on that plate is 6. So then what's the voltage on that plate? Well, 150 divided by 6, we can find that the voltage there is 25, okay, 25 volts. But if 25 volts are here, well, how much volts are left up top? Well, we know that the gain has to equal the loss. And so if I go up 30, I go down something and down something, or I go up 30 and down something and down something. Remember, these two things are in parallel. They have the same voltage. And since this is 25 volts, this has to be, both of those have to be 5 volts. So you just do another Q equals CV, and you know that the capacitance is 10 farads, and it's getting 5 volts, so it's got to store 50 coulombs of charge. And I do the other one, Q equals CV, it's got a 20 farad capacitance. It also just gets 5 volts, and it stores 100 coulombs of charge. And then we can confirm that some of the charge gets stored here and some of the charge gets stored here, but 50 and 100 is exactly the same thing as 150. And again, that's how this thing gets polarized. So the charge stored on this one, and again, hopefully you're okay with this, the fact that this is double the capacitance. 20 farads is double 10 farads. So it's not shocking that it stores double the charge, right? It's getting 2/3 of the total, it gets 1/3 of the total, but again, it gets twice this because it's got twice the capacitance. The capacitance is the ability to store charge. So I know each of their voltage drop, 5 volts, 5 volts, 25 volts, 50 coulombs, 100 coulombs, 150 coulombs, and then I could talk about the energy stored on each one of these things. The energy stored is 1/2 CV squared, or you can do a variety of other formulas, and you could look at all of those things. You could show that the total energy stored in the system is the energy of this plus this plus this, or you can just do the total. So we could do 1/2 the total capacitance. The total capacitance we said was 5 times the total voltage, which was 30 squared. Am I going to be able to do that in my head? So that's 30 squared is 900. 900 and half that is 450. And then I need 450 times 5. And 450 times 5, just so I actually don't mess this up on this video, is then 2250. So we're looking at a total of 2250 joules of energy stored in the total. And I want to show you that the total is equal to each one of those. So let's look at this one first. What's the energy in that guy? 1/2 its capacitance of 5 times its voltage squared, 5 squared, and it's not going to store much, right? So that's what 125 halves. So that's 62 and a half joules. The energy stored in this guy is 1/2 C. Oh no, I made that mistake. Check it. This is 1/2 CV squared. 1/2 C, that's a 10 farad, times then V squared was 5. So this was actually just 125 joules. Sorry about that. And then this is 1/2 its C, 20 times its voltage squared. Right, so that's a half of 20, which is 10. 10 and 25 make 250 joules. And then the energy stored in this particular one is 1/2 C, which is 6 times its voltage of 25 squared. Right, so that's what, 625 times 3. So that's 3 times 25 squared is 1875. And you better believe that the energy stored in the bottom capacitor, the energy stored in the right capacitor, and energy stored in the left capacitor does in fact equal the total energy stored in the system. Okay, so that was the capacitor example. Kind of walked through one that had a parallel in a series, and we found everything. We found everything about it. We found the energy stored on each one, the voltage of each one, the charge on each one, and we found the total capacitance of this branch. And then we added those in series to find the total capacitance, which found us the total charge. And then we realized that the total charge is the charge on this guy, which found us its voltage, which then, based on the loop rule, found us these voltages, and then we found those charges, and then once you know everything, then finding like energy is really easy. Again, hopefully that kind of helped you out for a concrete example with some numbers about capacitors.